Greetings! Let's talk efficiency. Or more specifically, let's talk optimization, because that's what the whole point of this is about. Now, a quick overview of my code. There are some things that I have in here that you are obviously not going to have because I've got some additional test cases set up to be able to demonstrate some things. But in general, this is pretty close to the solutions that you all will be coming up with for this assignment. So for the main, I'm checking to see if my argument's length is greater than 0. If it is, I'm trying to parse the integer. If I fail to parse the integer, I default back to the 100,000. This here is specifically so that way I don't have to mess with my configuration to swap back and forth between doing 100,000 and 2 million. So you will not have something manual like this, most likely. And again, you will have a single check. Now I'm creating an instance of prime check and then calling a method here. You could do everything in the constructor. It doesn't really matter too much. Personally, I think having it work like this, where I've got the class and I'm calling a method within the class, makes the most logical sense. And then as far as the stuff inside the class goes, the constructor doesn't do anything because it doesn't need to do anything. There's nothing we're needing to initialize here. And then for my find primes, fairly standard. I'm initializing count, my start time and end time, grabbing the nano time right before I initialize my for loop, and then ending the nano time immediately after the for loop. Generally speaking, when you are timing code, you are going to want to time it as tight as possible to the area that you're actually measuring. Because, yeah, okay, these two lines of code here, they're not really going to take up that much time. They will take up some CPU cycles to do this, but probably not anything measurable. And we'll get to the whole measurability thing here later. So I've got my start and end time tied up against the for loop, and then I do the calculation and print out how many primes were found and how much time was taken. And basically I'm just going through and every single number asking, is this a prime? Is 1 a prime? Is 2 a prime? Is 3 a prime? So on and so forth. Now the reason why I've got 3 different versions of find is one calls my unoptimized loop, one calls my optimized version, and then one calls my mega optimized version. We'll come back to these commented out lines here in a moment. And then here we've got the brute force solution. I check to see if it's less than 2. Is the number less than 2? Because again, that's part of the definition of a prime. It's a number greater than 1, an integer greater than 1. So check if it's less than 2, don't care, false. If it's equal to 2, well, obviously that is a prime number. I have to have this check here, by the way, because if I don't, otherwise 2 will fail inside of my for loop here, because 2 divided by 2 is 0, so I can't do 2 in this loop, but I do have to check to see if something's divisible by 2, right? So check to see if the value is 2. If it is, print it out, return true. Otherwise, I'm just going to go from 2 to less than the value, because again, I don't want to do the value itself. And just check everything. So again, if my target value here is 5, I'm going to say, is 5 mod 2 equal to 0? No. 5 mod 3, 5 mod 4. Nope, none of those became 0. So that means I'll make it to this point where I can print out the value and return true. Quick note, I know I've said in the past that I have a general philosophy of a function or method should have 1, at most 2 exit points. That is a general rule that I do try to follow, but sometimes you will find exceptions to that, and this is one of those cases. It just makes sense for the types of calculations and questions you're doing with primes, especially since we want to be efficient about it, to have multiple exit points. So I've got 4 exit points out of this function, which is fine. As otherwise I'd have to go through quite a bit more rigmarole and hoops to jump through to try to keep track of values and stuff, and then ask a series of questions down here. It also would lead to the for loop not being very optimized, because the instant I determine whether something's, not prime, there's 0 point in continuing on to check, and so on and so forth. So it just turns out in this particular case, I got 4 exit points to my function. What are you going to do? And before I go on to talking about the optimizations, let's take a look at how this code runs. Make sure that I am on 100,000, and I am. Run the code. Yeah, sometimes I get this little bit of error because of optimization on the CPU side. There we go. That's normally what I get every so often due to numerical errors. It won't measure lower than 33 milliseconds, and I can definitely sometimes hit lower than 33 milliseconds. The point here being, now that I've got same numbers for everything, is there's actually not much point to optimizing. The unoptimized version took half a second-ish. The slightly optimized version took a quarter of a second. And the massively optimized version took a 60th of a second. These aren't big differences, right? We have, a half-second pause. That's pretty noticeable. I mean, you definitely can perceive that. Quarter-second pause, it's a tiny little hitch. Again, perceivable. Yeah, no, you're not going to perceive 1/60th of a second pause at 60 frames per second. It's not going to happen. But it's not that big of a difference, right? 1001. That's a full second. It's this kind of speed difference is irrelevant. We don't need to do this. And that is one of the core rules of optimization. Don't do optimization until you know that you need it. In this particular case, if I'm just trying to find a couple thousand, 10,000 primes, I don't really need to know, I don't really need to have it optimized to the point where it takes me a 60th of a second to do it. It's kind of overkill. The brute force, which is really easy and really fast to write, again, we just saw it. There's not much to it. Is it 2? Yep, okay, that's a prime. Otherwise, just go from 2 to the less than the value and check to see if it's divisible. Done. Very easy. But what if you need to do more than that? What if I want to find all the primes up until 2 million? Well, that's a different scenario. Let me go ahead and get this running. And while that's running, talk about the first optimized version here. So, is prime optimized? Now, do I need to have this check here? Probably not. I'm not sure that that's actually gaining me anything. I'm not even entirely sure why I put that in there. I just did. Kind of instinctive. But I'm checking to see if the value is 2 or 3. If it is, print it out, return true, because that's obviously a prime. I then check to see if it's divisible by 2 or divisible by 3. And if it is, return false. And then because I've already checked for 2 and 3, I don't need to bother checking with 4. I'm going to start with I equals 5. And the actual optimization, the part of this code that's actually doing something, is this I plus equals 2. Sometimes it's very easy to forget because we're so used to doing I equals 0, I is less than whatever, I plus plus, that the only requirement for these components is this and this have to be evaluatable statements, and this has to evaluate to true or false. That's it. Those are the rules. I can put whatever I want in this end of loop action here. It can be a function. It can be a 17-stage equation. It doesn't matter. If it is something that I can write as a single line of code outside of the for loop, it is acceptable here. Always keep that in mind. So why am I doing I plus equals 2? Math. You get a lot of people that sometimes wonder, it's like, well, why do I need to take math classes if I want to be a programmer? Programming isn't about math. Well, it actually kind of is. This is a prime case here, right? If something is divisible by 2, that means it's an even number. Anything divisible by an even number is also divisible by 2, right? So if I have 50, yeah, okay, that's divisible by 10. But what is 10? 10 is 2 times 5, right? Which means if it's divisible by 10, it's also divisible by 2. Again, it's the definition of an even number. And so I don't need to check to see if my target value is divisible by an even number, because I've already checked if it's divisible by 2. So I can just cut out half the checks here, right? If something's divisible by 4, it is divisible by 2, because 4 is 2 times 2. Something's divisible by 8, it's divisible by 2, because 8 is 2 times 2 times 2, if I factor it out, so on and so forth. You see where I'm going with this, right? I don't need to check the even numbers. I have already checked. It's not divisible by 2, so the only thing that I need to worry about is it divisible by odd numbers? That is the only thing that I need to worry about at this point. And so I can just skip half the checks. And this should be done here in a moment. It's slowly working its way up. But you can see why optimization is important, right? I've been talking for a bit. Our elapsed time... Oh, there we go. It finally finished. Our elapsed time... I don't know how well you can see that, depending on your monitor size here, is 4 minutes and 2 seconds. That's how long it took me to check up to 1 million using the unoptimized, the optimized, and the majorly optimized versions. And if we look at our timings here, it's pretty drastic. The brute force method took 160 seconds-ish to complete. That is 2 minutes, 40 seconds. Because I cut in half the number of checks that I actually have to do, the small optimization took 80,000. Or not, it took 80,000 milliseconds. It took 80 seconds, or 1 minute and 20 seconds. Right? So 2 minutes, 40 seconds, 1 minute and 20 seconds. Adds up correctly. The major optimization took 200 milliseconds. Fifth of a second. Much, much faster. And so now the question becomes, well, does it matter? And the answer is starting to become, well, kind of yes. If I actually need to find hundreds of thousands of primes, I am going to want to use the optimized version. Because while there's still a perceivable amount of time here, it's a lot better than the alternatives. But how do we get here? Right? That's the extra credits. Like, how do we check for all of the primes from 1 to 2 million in under a second? How do we get there? Well, again, the answer is more math. I don't go from 5 to 2 million. I go from 5 to the square root of whatever I'm checking. How does that work? Well, let's take a look at some spreadsheets. Everybody's favorite, right? Change that down to 29. So let's say I'm trying to determine whether or not 29 is prime. Well, it is, because I've got here the full thing here. Remember, divisor, that's what you're dividing into. So 29 divided by 2, 2 is the divisor. The quotient, which I think I spelled correctly, is the number that's on top of the divisor box. And of course, remainder is what you got left over. So 29 divided by 2, 2 goes into 29 14 times with a remainder of 1, so on and so forth. So we can see the fact that none of these remainder values are 0, that 29 is prime. In comparison, 30 is not, because there's multiple zeros in the remainder column. So if I do the full check, it would take 27 checks in order to validate that 29 is prime using the brute force method. The square root of 29 is 5 and some change. If I round that up, which you don't have to do, by the way, I just like being paranoid, but if I round that up to 6, so I say I'm only going to do my divisions up until 6. And if there's no zeros, it's prime. So I'm only doing 5 checks. Well, it works, but why does it work? Remember the rules of division. You can swap the quotient and the divisor, and you will get the same answer. 29 divided by 14 is 2 with a remainder of 1. 29 divided by 9 has a quotient of 3 with a remainder of 2. It's a little bit easier to see maybe with 30. And more specifically, oops, not those two values. These two values right here. 30 divided by 5 is 6, remainder is 0. 30 divided by 6 is 5, remainder of 0. Once I've divided by something, I don't need to continue doing the checks where the quotient equals divisors that I have already done. And I can prove this. Let's take a look at 291. Square root of 17, so we'll do our checks up until 18. Oh, there's a 0 right there, so I know it's not prime. So let's move that up to 293. Again, square root of 17, so I'm going to do my divisions up until 18. There are no zeros here. And 15, I've already done. 14, I've already done. I don't need to do any more checks. And I can prove this I'm going to borrow the no-op here. I can prove this by setting in some breakpoints. So here's some bonus breakpoint information. I will expect you to know how to do from this point forward. So I'm going to switch. Sorry, I forgot to narrate a step there. I'm manually switching to debug mode up here in the corner. And what I am going to do actually is prime no-op here. What I'm going to do is I'm going to put in 2 breakpoints. I'm going to put in a breakpoint here, and I'm going to put in a breakpoint here, so I can tell whether or not I'm about to say 293 is not prime or 293 is prime. Now I can't leave the breakpoints like this, because otherwise they'd break in at every single value, and I'm not hitting continue 290 some odd times. But because I'm in debug mode, and normally by default you'll be looking at your variables list, I can go to breakpoints, And I can select these breakpoints and I can put in a conditional. So I'm going to check conditional and I'm going to say, what do I want? I'm looking at value. So I want to say, is value equal to 293? And then I'm going to use this little drop box here to set it. And I'm going to do that for both of these. So I'm going to set this one as well, conditional, value equals 293. So what I've done now is that these breakpoints are only going to activate when value is equal to 293. Now I can run this, so run debug. And oh hey, look at this. It is broken in. I don't know why it's sometimes. There we go. Sometimes it breaks in when it's not supposed to. Like it takes it a moment for the conditionals to kick in. I have noticed that it's an odd thing in clips. I just had to hit the continue button once, and now it's stopped again. And value is 293, which means if I've reached this point in my code, yes, 293 is prime. So that's how the major optimization works. Yes, I want to get rid of these breakpoints. I don't want them anymore. So coming back down here, I am finding out what is the square root of value. I am doing a ceil operation to round it up to the next whole integer, regardless of what the decimal point is. Casting it to an int, because it needs to be an int for my for loop. And then checking, it's like I'm only going to go now from 5 to max val. And now instead of a linear growth, I have a logarithmic growth. So, it takes a lot fewer checks to be able to do this. You have to do this in order to get the 2 million check to be below 1 second. Now, are there additional optimizations that we can do? There are, actually. The square root function is perhaps not the most efficient of things. I could skip the ceil operation and just immediately cast the square root value to an int to drop off the decimal point. That might help me with a little bit of efficiency because I have to do this every time. You can actually write your own square root function. The default square root is fine enough, but you can do an approximation, a fast approximation, because we don't need the exact square root value. A fast approximation would be just as good. So you could do a fast approximation method, which would be much faster than the default one. There are things that we can do. Is it necessary? Well, I mean, it took, 200 milliseconds, a fifth to a quarter of a second to do the calculation? No, not really. But what if we wanted to find all of the primes going up to the maximum integer value? Do a few little comment out here real quick. I'm not actually going to let this run to completion. And I'll explain why. And there's one other thing here that I need to change. And I'll explain why I need to change it here in just a moment. Again, I don't technically need to do this because I'm not letting this run this long. I need to uncomment that line or it will never finish. Off it goes to the races. And you can see it's moving pretty quick. It's like, again, we're already at 4 million here. But we need to go to 2 billion and change. The fact that we're only on 7 million is concerning. Also, why did I have to do this? Well, here's the reason. What is integer.maxValue? Think back to Python. There was a reason why we went over binary math. Remember how negative numbers are represented? The largest bit, the most significant bit, or if I'm looking at it on a sheet of paper, the bit that's on like the left-hand side. So if I've got a sequence of bits here, that determines whether or not a number is negative. So this would be a positive number. This would be -1 if I'm doing 4-bit numbers here. So if I have max int, what does that mean in binary? Well, it's positive, so that means this leftmost bit is going to be 0, and then I'm going to have 31 ones following it. So first bit will be, the leftmost bit will be 0, then I'll have 31 bits all turned on to 1. What happens if I add 1 to this number? It becomes this. This is the maximum negative value. This is integer.min value. This is -2 billion and change, because it's going to be a 1 and 31 zeros following it. Oops, that's not good, but why is this a problem? Well, let's look at how I have my for loop. I'm going from 1, I is equal to 1, to I is less than or equal to the limit, because I have to check the limit. It's like, yeah, 100,000 or 2 million are obviously not primes, but if I'm writing my code generically to be able to handle any number that's thrown at it, I need to check up into the limit, because what if I want to check up to, 100,001? So if limit is max int, remember how for loops work. This is why it's important to understand what the code is doing. This is why you do not want ChatGPT to write your code, because otherwise you would never understand why this fails. Limit is max int. It is a 0. Let's say it's the last cycle. It is the max int value. So it's 0 followed by 31 ones. I check to see, is that prime? It's not. This line doesn't exist yet. So we check, it's not prime, and then we hit the end of the loop, and this statement is executed. The end of loop statement is always executed before you make the check. That is how a for loop works. Well, I have max int. Max int plus 1 causes an overflow, basically, and now I have min int. I is -2 billion. Well, -2 billion is certainly less than 1 billion, so we're just going to keep on going. And I discovered this because the first time I ran this, just to see how long it would take, started it up, went, fixed breakfast, came back, wasn't done. All right, okay, fair enough. Went to do something else, came back. We're about an hour in at this point. I was like, still not done. Went off, did something else, came back. We're about 2 hours in at this point, and I'm like, all right, something's wrong. And then I noticed that I had multiple printouts of 2 and 3 because I had actually disabled this part right here because I was concerned about, memory issues of this running for however long it was going to run, going all the way up to 2 billion. I was concerned that that would not only potentially cause memory problems, but could affect the timing. I didn't want the time, include console output in the timing, so I just turned off this. So I just had 2, 3, and then it looked like the program froze. But it should have only printed 2 and 3 once, because the only way that it should print that is you come through with 1, 1 is less than 2, false. You come through with 2, print it out, come through with 3, print it out, come through with anything greater than that, and we fall down into this stuff, and like I said, I had this commented out. So why was I seeing multiple 2s and 3s? And that's when I started doing the debug checks to try to figure out what was going on, and that's when I discovered that I was resetting, and it clicked on me at that point once I saw that I was resetting. Oh, right. Limit is max int plus 1 is min int. I have an endless for loop. It's difficult to get an endless for loop, but it is possible. And so that's why I have this line in. I detect, after I've asked the question, is, I prime. If I is equal to max value, I break out of the for loop. I have to have that line in there, otherwise my for loop will not end. I'm going to go ahead and stop that because that took about 36 minutes to actually run. And yeah, I'm not letting this sit for another 36 minutes. How many primes is that? Well, it's that many, which, by the way, is one of your answers to the quiz. Now, does optimization matter? Well, again, it took me 36 minutes. The unoptimized version is about 400 times slower than the optimized version. That means if I let this run on the unoptimized version, there's your other answer, by the way, it would take about 10 days of my program running 24/7, uninterrupted, non-stop, to be able to calculate those 105 million primes. 10 days. Does optimization matter? Well, in this scenario, yes it does. But again, we don't want to do this optimization unless we know we need it. Do we need to calculate out so many primes? We will be coming back to this, however, because there is one very important optimization that I can make that actually covers something that we need to talk about for this class. Let me get back into code here. Let me start this back up. And that other optimization is CPU. I'm not really using all of my CPU cores. I've only got about 25-ish% utilization, and that's primarily because I've got a bunch of junk open on my computer. If I was actually to go through and close out everything that I have open, my CPU utilization would be a lot less. But I'm nowhere near close to actually using all of my CPU because this is a single-threaded program. I'm not using multiple threads. If I was to use multiple threads, that would improve the speed of this program by a lot. I've got 12 logical processors. I could spawn an additional 11 threads. But that has its own set of headaches, which we will deal with later. Much later. Just want to bring it to your attention. And again, for one final time, for the answers that you will need, here's that information again. Make sure you enter in exactly as it is written. And with that, that concludes our little discussion on how do you optimize finding primes. Have a good day. I'll catch you on the next one.